Alright, so on this lesson what we want to do is we want to talk about the definition of what a logarithm is. We're going to be doing a lot of things with those. And we're going to let some base, b and y, be positive numbers, where b cannot be equal to 1 because 1 to any power is just 1. So the logarithm of y with base of b is denoted by the log of base b of y and is defined as follows. The log base b, right here, log base b of y equals x if and only if b to the x equals y. So these two guys go together, all right? They are inverses of each other, and we're going to discover more how that works. So, it's the log base b of y, all right? And here's some little rules over here in the yellow box of how bases and of how logarithms work. Any log of 1 is equal to 0, and any log where the base is the same as the number on the inside is equal to 1. So using what we know, let's go ahead and simplify some of these expressions. Log base 2 of 8 equals 3. So how does this look? Well, this guy looks like the base, which is 2, to its exponent, which is 3, and it's equal to 8. So that's all there is to it. We're just changing from log form to exponential form. Another way to think about a logarithm is this. A logarithm is equal to its exponent. So a log is equal to its exponent. And that might help you keep everything a little bit more sorted out as you're working these problems out. But it's all pattern-based stuff. So it's going to be the same pattern over and over and over and over again. So if I've got a log base 4 of 1, a log base 4 of 1, then 4 is my base. My exponent, my log base 4 of 1, equals the exponent, 0, and that equals 1. Okay, what about this guy down here? Log base 12 of 12 equals 1. So what does that look like? Well, my base is 12, and my log equals my exponent, and the number inside the log is 12. So these all work out really, really well. And then the last one is my log of base 1/4. So my log of base 1/4, okay, is equal to its exponent, -1, which is equal to 4. And remember, on this guy, when I send that -1 through there, I'm going to have 1 over 4 to the -1, which is that cat right there. Okay, so let's just evaluate some of these logarithms, and all of these clean up really, really, really nicely. So log base 4 of 64, what do? Well, just think to yourself, what number has a base? Well, think about this. 64 is what number to what power? That's the best way to think about it. And 64 is equal to 4 to the third power. Okay? And so if I've got 64 is equal to 4 to the third power, I've got a log base 4 of 4 to the third power. And anytime that happens, this guy is going to just equal 3. And we just saw in the previous slide where if the base and the number inside the log are the same, this guy right here and this guy right here, then you get whatever the exponent is. Okay? Well, let's look at the next one. It's a little bit different. So on that next guy, we've got the log of base 1/5 equals 125. So what power of what number is equal to 125 is kind of what we want to try and think of. And so on that, we would say that 125 is equal to 5 to the third. Okay? Well, that's great, but it doesn't get me to that base of 1/5. So how could I get that 5 to the third to look like a base of 1/5? Well, let's just be a little creative and follow our rules here. If I take 1/5 and raise it to the negative third power, that will also get me 125. And if you FOIL that, if you look at that, that's going to be, 1 over 5 to the negative 3, which goes back to the step right above it. So right here, this negative 3 would go on the 5, okay? And then that gets me to this guy right here. So that we haven't done anything crazy. What we end up with, though, is log of base 1/5 of 1/5 to the negative 3 power. Well, guess what? My bases are the same. My base and the number inside my logarithm are the exact same. So my final answer is just going to be negative 3. All right, let's look at the next one. So I've got log base 5 of 0.2. Oh boy, so what is 0.2? 0.2 is the same thing as 2/10, which is the same thing as 1/5. So using what we know about the previous problem, I need that 1/5 to be equal to 5. All right? And how do I do that? I just say that 5 is equal to 1/5 to the negative 1 power. When you look at that, then you're going to get a 5. So what I really have is a log base 5 of 1/5 to the negative 1 power. And so again, since my base, oops, that should be 5 to the negative 1. What have I done here? This right here should be 1/5 is equal to 5 to the negative 1. There we go. There we go. So if I've got 5 to the negative 1, this changes just a little bit. Got a little ahead of myself. So this is actually going to be 5 to the negative 1 power. And since the base is the same as the number inside the logarithm, then I'm going to get negative 1 for my answer. Okay, let's look at this last guy, 36 and 6. So I've got a base of 36. So how do I go, like what number to what power goes from 6 to 36? Well, if I look at 36 and I take the square root of it, that's the same thing as 6. Okay? So what I'm going to have is 36 to the 1/2 power, which is equal to 6. So my logarithm then looks like log base 36 of 36 to the 1/2 power. And if I've got that, log base 6 of 36 to the 1/2 power, what do I have? Well, again, I've got the number and the log the same, so that's just going to give me a 1/2. All right, before we can solve this one, we've got to talk about a couple of things, and that is the natural base and a common log. So if I have a log base 10, we never write a log base 10 as a log base 10. We always just write it as log x. That's a common log. And then any log that has a base of e, we're going to write as a natural log. So they still have all the same properties we're working on. There's nothing different here. But let's go ahead and look at what some of the things that might happen is this. If I have a base and in that exponent is another log with the same base, so this would be 10 to a log base 10. The bases and the logs cancel out, and this guy right here just drops me off with the 4. That's it. That's all there is to it. They cancel each other out. If you've got a base raised to a power with a logarithm of the same base, that's what you get. Well, what about log of base 5 of 25 to the x? Well, Think about 25. 25 is 5 squared, right? And so what I do is I kind of reverse engineer this guy. I'm going to have a log base 5 of 5 to the 2x. You see how that happened? I can send that 2 through there. I still have 5 squared. Okay, so I'm kind of going a little bit backwards. If you want to think about it this way first, let's see here. Let's think about it like this. What if I said I have 5? Whoa. Oh. All right, here we go. For real. Five squared equals 25, so I would have log base 5 of 5 squared to the x. Okay? So how does that work? Well, remember, if you multiply your outer exponents with your inner exponents, right? So I can take that 2 and pull him out, and I get log base 5 of 5 to the 2x. And now notice that my base and the number inside the log are the same, so that's just going to give me 2 to the x. And that's really all there is to it. And somehow I've erased my first guy over here, and he's just a 4. Okay, so if we're going to find the inverse of functions, then we have to undo what's being done to them. And if I've got an exponential function like this guy right here, the inverse is a logarithmic function. So when I find this inverse, what I'm going to look for is the base. And the base in this case is the 6 right here. So I'm going to have a log base 6. And remember, a logarithm is equal to its exponent. So the exponent on this is x. And then the y goes inside the logarithm. So this would be how this guy pops out. And since it's an inverse, then x and y have to trade places. So what I'm going to end up with then is log base 6 of x equals y. So this guy right here then would be the inverse. If you're looking at on the other side, we've got this y equals the natural log of x plus 3. So again, and I didn't switch my x and y right at the beginning, so let me go ahead and do that this time. So I'm going to have x equals natural log y plus 3. Okay, and then how does this change? Well, a natural log is a log base e. A natural log is a log base e. So what I really have is the base, and the logarithm always equals the exponent. So my base is e, my exponent is x, and it's going to equal y plus 3. And so we're almost done, because usually whenever you graph something you have y all by itself. So we would have e to the x minus 3 equals y. And that's my inverse on that guy. Okay, real quick, these are the parent graphs for logarithmic functions, okay? And the logarithmic functions are these guys right here in, this one's in red, and this one's in red right here, okay? Logarithms are inverses of exponentials, so they go the reverse direction, okay? They have that reflection over y equals x. They undo each other. So any log graph you create is going to have this sort of shape. Okay, now this is for bases larger than 1. Okay, you cannot be equal to 1. We're going to be larger than 1. For any base that's between 0 and 1, you're going to have this shape every single time. Every single time. So you on the first guy right here, okay, the y-axis is a vertical asymptote, because my logarithm will never, ever, ever cross it. When you look at this guy right here, my y-axis is a vertical asymptote because this graph will never, ever, ever cross it. For all logarithmic graphs, the domain will go from 0, but not including 0. The domain will go from 0 to infinity. Every single logarithm you have, the parent function will go from 0 to infinity. The range for these guys go from negative infinity to positive infinity. And again, this is for your logarithm graphs that are your parent functions. And then if these get translated, our domain will change just a little bit, but the range will go from negative infinity to positive infinity on all of these. So here we go. We're going to graph y equals log base 3 of x. So let's pick powers of 3 to work with, because those will undo each other really, really nicely. And so here's how this is going to work. I'm going to let log base 3 of 0. I'm going to let x equal 1. And remember, this is going to be 0. So I plot the point 1, 0. Then I'm going to let x be equal to 3 to the first power. So that gives me 3 to the first power, which is 1. So when x is 3, y is 1. And then I'm going to let x equal 3 squared, which is 9. Okay? So when I put 3 squared in for x, I get 2. So all the way out here at 9, I get 2. So my graph is going to look something like this. Okay? The domain for this graph is going to go from 0 to infinity. The range is going to go from negative infinity to positive infinity. Okay? What about log of 1/2? Well, that's going to be a little bit different. So I'm going to do this, take the same steps that I did a second ago. And what I'm going to have is, I'm going to have a log of 1/2, base 1/2 of 0, and that's going to be 1. So I go to the point where x is 0, or when x is, when x is 1, y is 0. I wrote that wrong again. Okay, we're going to let x equal 1. That means my exponent has to be 0. So then what I'm going to do is look at the powers of a half. So I'm going to look at like 1/2 to the first. I'm going to look at 1/2 squared, 1/2 cubed. Okay, these are the powers that I'm really interested in. And so in order to do those, I'm going to pick a base that I know. And so when I come back down here and I let x equal 1/2 to the first power, that's 1/2. And so what happens is, if I get 1/2 to the first power, that's just 1. So when x is equal to 1/2, I'm at 1. And so notice this is going to take me up away. And if I do 1/4, I'm going to go up again. So let's also consider looking at negative powers. Okay, let's look at negative powers. So what if I do, like, say, 1/2 to the negative 2? Okay, 1/2 to the negative 2. Well, then when x is equal to 4, okay, when x is equal to that 4, my y value is going to be equal to negative 2. And since it's 1/2, then the next one would be when I've got that negative 3, 1/2 to the negative third, that's going to be 8. So I would come out here to 8, and then down to negative 3. And there's that graph. So on this particular guy, the domain goes from 0 to infinity, and the range goes from negative infinity to positive